Everyone, welcome to this workshop. There is a lot going on here. Unfortunately, I don't have this display mirrored, so I'm going to be speaking like this. I just installed a new operating system and having those troubles, but it should be fine if I just kind of talk through it up here. So, welcome to my talk, or workshop rather, Types of Specifications, an introduction to type-level programming in Haskell. This is going to be a very broad workshop where I kind of assume that you know what Haskell is, you know what algebraic data types are, and we'll get to kind of the prerequisite knowledge in a bit. But I'm going to kind of start from kind of the beginning and kind of talk about certain things that you kind of really need to understand very well in order to even understand what type-level programming is or why we would want to do it. So without further ado, does anybody have any questions about the setup, or need to install Stack and need to clone the repo and start building the project? Okay, cool. So I'd like to know who is talking to me or who's giving the workshop at any time. So I'm a software engineer at Freckle. It's an education tech startup. We use Haskell on the back end, USOD. I have been programming in Haskell for about 5 years. I've been using it professionally for my entire career, luckily. So yeah, and that's where I am now. I am a hardware hobbyist, and I have free time. I like to play with Arduinos, and I kind of like the intersection between typed functional programming and the bare metal, and kind of crossing the divide between those two things. So I like to explore that in my free time. I go bouldering or top roping, which is a type of indoor climbing or outdoor climbing. That's kind of like my main form of exercise. I read a lot. I'm probably reading 30 minutes to an hour and a half a day, from nonfiction to fiction, whatever is kind of popular at the moment. And then I also love to drink Northeast IPAs. That basically sums me up. I mean, I know it's like, you might say, why are you telling these arbitrary facts? It's like, this is all I do in my whole life. So.
But the people only remember the first and the last one.
Right. So, and I'll drink IPAs. I'm good with that. So, I'd like to start off with a quote from Leslie Lamport that says, "Everyone thinks they think, but if you don't write it down, then you're fooling yourself." Which means, if you can't really manifest, yeah.
Do we have Slack channel?
Not for this. There's a Slack channel, yeah. It's B15115. So yeah, I'm a big fan of specifying the code that I want to write, and luckily Haskell lets me specify my programs with the type system. So I'll give you a brief overview of what this workshop's going to look like. I'm going to give an introduction with lectures and exercises interspersed. There's not going to be a clear, distinct lecture section and a clear, distinct exercise session, because I think that's a little bit more dynamic. I give you 5 minutes to do it, and then we can solve it, and nobody's stuck for 15 or 20 minutes. So then I'm going to talk about what type-level programming is, give some lecture and exercises. I'm going to give kind of a final example of type index lists. There's a few ways we can do this, so it's not just length index lists. I talk about heterogeneous lists and how we build these things from the ground up. And then maybe if we have time, I don't really know how long this is going to take, but I would love to talk about first-class type families, which is a way of treating type families as type-level functions that can be partially applied, which you actually can't do, and we'll get into that later. And then also maybe type-level state machines. But honestly, the discussion bit, I don't really think we're going to get to, because there's a lot of ground to cover. So yeah, here's the start of the introduction section. I want to ask the question, what is a specification? And an answer with that, a specification is a formal description of program semantics. What do you want your program to do? What does your program mean? So there are a lot of types of specifications. There are decision tables, business requirements. You probably maybe do RFCs at your company. Writing documentation is a type of specification. And then finally, we have types. And this is probably the easiest type of specification, because in Haskell, we have these just embedded in the language itself. So what is a type? well, there's a lot of different ways to describe a type, but ultimately it's metadata associated with a particular region of memory locations that describes the structure of the data content of those memory locations. Or you could say it's a set designating the shape, form, or structure of language level values. And ultimately the goal of types is to make invalid states unrepresentable. We want to constrain the domain of values on which our program can operate. So in Haskell, there is this notion of, there's this separation of values, types, and kinds. And these are kind of like different levels of, they're kind of all related. So values describe data, so we can have the integer 17, and then however Haskell chooses to represent that in memory, that's kind of what we're talking about. And 17 is this abstract representation of really just bits and bytes in memory. Types describe values. So if I have the type int, then I have a set of values that inhabit that type. So types describe the set of values that can be represented in that place. And then finally, in Haskell and other dependently, well, Haskell's not a dependently typed programming language, but independently typed programming languages as well, we have kinds that they describe types. So you have the kind star, which can describe types of like int or maybe bool or the function from A to B. Or we have kind star to star, which has, the types that inhabit that are maybe or either double, like a partially applied either type, a reader int, which is waiting for a value. And I want to just go back really fast. Yeah, here we go. I skipped something. So just before we get into the types and the kinds, there's some assumed prerequisite knowledge I think you have. And unfortunately, if you don't have that, it's going to be a little bit harder to follow along, but you're not going to be like completely lost, hopefully. I hope you understand the difference between static versus dynamic type systems. Haskell has a static type system. I hope you know what I mean when I say a type signature. I hope you know what algebraic data types are, which is kind of like the cornerstone of the Haskell programming language. What type classes are, which is a very canonical way we use to describe interfaces in Haskell. Given a certain type, it implements these set of functions that we can call using the values of that type. There are constraints, which are ways we can constrain the types to which we can apply our functions. And finally, I want you to know a little bit about what functors, applicatives, and monads are. They're not necessary for this talk, but I might drop those words, and I hope you understand what I mean when I say those. And finally, I hope you know what Haskell is, and if you don't, it is a strong it's a strong statically typed programming language that has algebraic data types as its foundation, sums of products. For those of you who understand the underlying mathematical structure of those types. There is a designation in Haskell between pure versus impure values. And pure means that there are no side effects that happen when we call these functions, and impure values may have a side effect when they're evaluated. They may talk to a database or send a network request. And finally, I want you to understand, or I hope you know what GHC is, which is the kind of canonical Haskell compiler. There are other Haskell compilers, but this is the one that won. There was a fight, and this one emerged victorious, and this is the only compiler that people use nowadays. And I want to note that it's extensible. So in this talk, or this workshop, we'll be using a lot of language extensions. And these are ways that other programmers have extended the Haskell language to maybe alter their syntax or alter the way the type checker interprets your program. So getting back to the values, types, and kinds. So in Haskell, there's this difference between values, types, and kinds. And without repeating myself, values describe data, types describe values, and kinds describe types. So in your sort of imaginary prelude session, you can see that if you ask the Haskell or GHC the type of true, it'll tell you that true has type bool. These two colons mean has type. If we have the type of just Haskell, you can see that the type is maybe list of characters. The type of 5 is num_p for all p. So this is an example of a constraint. So I haven't told GHC the type of this number, so it just knows that like this is a type that has the constraint, or that implements the type class num. The type fmap we can see is for all functors f. It takes a function from a to b and a value in the functor context a, and then returns fb. And then the type of the bind operator in Haskell, which you can read.
By the way, are these slides public?
They are public. I didn't post the URL.
In the Slack channel.
Yeah.
I can post it in the real.
Yeah.
Just type in what you have.
Yeah, sure. That'd be great. So there's a notion, to construct values in Haskell, we want to use value constructors. And this is kind of your canonical definitions of algebraic data types, where the maybe type is a sum type of just A or nothing. And the either type is either left of some type A or right of B. And we can define new types that are, maybe this is just maybe a wrapper around some monad. And we can see in an example prelude session that the type of nothing is maybe A, the type of just is A to maybe A. And for instance, on the bottom, the type of T is, it's a value constructor that takes a value of type MA and returns a value of TMA. And then we also want to be able to ask GHC what the kind of types are. So for instance, the kind of int is kind star. The kind of maybe is from star to star because it's a type constructor. It's waiting to take a type, to be applied to a type before it returns a kind of fully saturated type of kind star. A quick note is that values in Haskell, the only kind of type that has value level inhabitants is kind star. So if there is a type that has kind star to star or star to star to star that's waiting to be fully applied, there are no values that inhabit that type. We cannot manifest those types at the value level.
Can you say that one more time?
Yeah, right. Yeah. So only types of kind star have value level inhabitants. Right. So if we just have like the type maybe, it's waiting to be applied to another type before we can manifest any type of value. Right? There are no values that have type maybe. There are no values that have type either bool. And just as there are no values that have type either as well. So that gets us to type constructors. So just like in the previous slide, now we're not talking about the just or nothing or left or right or the T. We're talking about the either or the maybe or the app, right? These we take the kind of, and these are what we call type constructors, just as I mentioned in the previous slide. And you can see the very last, these kinds, really the kind language in Haskell is all about, it's either star or star to star, star to star to star. Because star is the kind of just, fully saturated type. So,
Like errors.
yeah, basically, right. So how many types does this type constructor need to be applied to before it is a type that has value level inhabitants? So if we look at the kind of app at the bottom, Haskell actually has a kind inference. So note how we didn't denote the kinds of any of our types in the type constructors, like TMA or app, MF, AB. We can just look at this very confusing record type signature to some people and see that GHC infers what the kind of these types are by the way we've used them in the definition. Since F is parameterized by A, the F, which is the second position in the app type, we know is star to star. But see how M takes two type constructors, two types as argument. So thus, GHC infers that it's kind star to star to star. And since the record fields X and Y are describing values, that's how it knows to infer what the kind is. Because if MAB wasn't fully saturated, we just couldn't give Y the type MAB. So thus it knows that MAB is a fully saturated type. It ends up being of kind star when it's fully applied. And thus, in the declaration of app, the M infers that it's kind star to star to star. And I know already, this is kind of confusing if you're not used to using Haskell. But unfortunately, you kind of have to get this before we can even talk about type-level programming. So, yeah, sure. Mm-hmm.
So here, if I'm looking at the kind of f, it says star to star because it's taking an a. So certainly that like f of a must be kind star to come out, but nothing sort of restricts a to be something else. So like f could have taken something from star to star to star to star, and a must have been star to star to star. Like how is it concluding that a must be kind star just from that record syntax?
I'm not entirely sure. It could be because of the kind inference algorithm that's done. Otherwise you could never infer a kind, right? Because it could just be of infinite kind if you don't give me any information. So I think you could annotate, and I'll show that on the next slide. You can tell GHC the kind of it, but it also tries to kind of infer the simplest kind that it can for the types that you go in it. So we're going to introduce our first language extension called kind signatures. And all this lets you do is annotate in your type constructors, in the definition of your data types or new types, the kind of the types that you want to use in the body of your data type definition. So you can see the maybe type has type A. The A in the maybe type constructor has type star. The A and B in the either both have type star, because otherwise, we're talking about values now. The left and right are parameterized by A and B, and in order for values to inhabit in order for these to actually be values, the types A and B must be kind star. And you can see the TMA type.
Wait,
yeah.
Can't the compiler derive all these?
Yeah. So it did derive that here. I'm just noting that you can also annotate it explicitly. Yeah, so this is just redundant information right now. Later on, it will be more important that we know that we can denote the kind of types in the. Yeah, sorry.
Yeah, I think I might be confusing myself, but you can have a maybe of a function, right? Was a function considered
Yes.
inhabited?
Yes, because a fully saturated function arrow, int to bool, that takes no more types as arguments. It is of kind star.
Right, but you can't do as maybe of arrow.
Right, yes, because arrow is not fully saturated. Yeah, exactly. So I hope everybody was able to follow that. We are going to get into a little bit more specific examples, and this is going to be the first area where you'll have some exercises to do. Now, since this is a workshop, we are going to have periods of exercises. I want you guys to try your best with them, and I want you to go ahead and open the file that's src. I should actually have posted this in Slack. So the file that I want you guys to open is in the source directory. It's in the type level subdirectory, exercises, intro, GADTs. So I can, let me go ahead and post that in the Slack channel. It is, yep, source, type level, exercises, intro, GADTs. Now we're not gonna do it just yet. We're not gonna do the exercises just yet. I'll have a slide when the exercises come around. But yeah, just go ahead and have that slide open. There should be a lot of type errors. I noted earlier, but maybe everybody didn't hear. It shouldn't compile right now. If you've tried stack build and you got a lot of type errors, that's right. That's correct. So your code shouldn't compile. You will make it compile, hopefully. So this is kind of like the real intro to type level programming. You had to understand what types and kinds are and values and all their relationships before we can talk about type level programming, because this is kind of where it all happens, at the type level. So instead of writing code that describes values and we give types to, we're actually going to write types that have kinds, and we're manipulating types, and our type level functions are going to have kind signatures. Just as your value level functions have type signatures, our type level functions are going to have kind signatures. But
Will be values.
kind of, yes. So all this evaluation will be done at compile time, but we'll get into that, right? So we're going to start off with the basics. This is actually not yet type level programming, but these are the tools that you need to do kind of more interesting type level programming. And the language extensions that we're going to be covering are multi-param type classes. It's pretty simple. It just means that we can have multiple parameters to our type classes that we define. And finally, GADTs, and I'll get into what that means in some previous slides, the next slides. So there is this notion of a phantom type in Haskell. And really, it's just an indexed type. And when we say index type, we mean that there's a data type that is parameterized by some type that does not occur in the value definition. And if that's confusing, we'll get to it. It allows us to attach extra information to all values of a data type without modifying the structure of the values that inhabit that data type. Notably, the phantom type arguments attach this information to all constructors. So if there is this kind of type floating around in the type constructor, you can see here, this is a canonical example. It's used as like a canonical phantom type. And we'll get into what phantom types are used for in a little bit. But you can see that the proxy type it's a type constructor that takes another type as an argument before the type is fully saturated, before we can manifest a value proxy. And note how the A does not show up in the value definition of proxy. Otherwise, it'd basically just be the identity type. You know, we'd have like identity A equals identity A. Yeah?
So it's kind of like a const function for types.
Right, yeah, kind of. So it takes the type, but then the values ignore that type. Yeah.
But, question? But if that's the proxy A is still a type constructor, right? But this, even though that A doesn't exist on the
Yes.
data level, that's somehow still encoded? Can I still retrieve that information later on?
Yes, in the type signatures, yes. So the A stays in the type of proxy, but the proxy values do not have like a field of type A.
So this sounds familiar in the sense that if you're saying let X equal the empty list, you can't derive what kind of contents that list might contain.
Right.
So you have to declare it explicitly.
Yeah, exactly, just like the nothing in just, where it's... Yeah.
So I assume this is used only at compile time?
Yes, exactly. So type level programming is going to happen completely at compile time. And there's a caveat to that answer where you can do kind of like, you can reflect types into the value level and also make the types of functions depend on values, but that's kind of beyond the scope of what we're talking about right now. We might get into that at the end. I don't think so, seeing as the time is going. So here's an example. So I want to kind of motivate phantom types. So let's say we have this distance type where we want to have some distance units and we want to, manifest some amount of those distance units, right? We could construct a distance unit value or distance unit type that's inhabited by the values miles and kilometers. And then in our distance values that we construct, we will supply a distance unit to describe that distance value. So you can imagine, I didn't give an example here for some reason, but you can imagine distance miles 20, right? So that means we have basically like 20 miles of distance. And we might write a add distances function that takes two distance values and returns a distance. But we kind of have a problem here because we don't know how to add two distances of a separate distance units, right? We don't have this conversion function built in. So basically what we're going to have to do is say, like, if the distance units are equal, then we are going to return the distance value where those two distances are added, the distance values are added with the distance unit that was provided, or else we're going to have to, throw an error because we don't know how to convert it. And this is the problem. This is really annoying code. What we'd really like to do is to add two distance values and kind of have this conversion happen maybe implicitly if we find it somewhere else. So we want to write this conversion function that converts distance units, converts one distance value to another distance value. But if you look at the type here, this doesn't really we can't do this because we don't know what distance units we want to convert from, and we don't know what distance units we want to convert to. So we could wrap the underlying conversion function with like a distance. So give me a distance and a distance unit, and I'll return a distance which the original distance has been converted to that distance unit. And sorry, it really should have showed both of these at the same time. And then we have this very granular function that takes some distance value, a distance unit, another distance unit, like so some distance unit to convert from, some distance unit to convert to, and then finally resulting in the converted double, the distance value. So you can see here, we take some value v, and we're converting from miles to kilometers, and we multiply that value by 1.609.
Is it okay for the compiler that there are two functions which are named the same? Convert.
No, this should have been commented out, the convert. Yeah, it wasn't, it was kind of more of like, this is not the type that we want. Yeah. So yeah, not all the code snippets are going to be runnable, unfortunately. That's like a lot more work. I kind of focus more on the content than the delivery. Right, so this is kind of annoying though, because we have to get really granular. We have to pass around these distance unit values, and it just seems like more complicated code than we should have to write. So enter the phantom type. Instead of having a distance unit value that really only exists to describe what unit the distance value should be interpreted as, we can parameterize the distance value. So this is a new reification of our distance type called p-distance, like phantom distance, where we have this type parameter a. So now all we have to do is carry around a distance value, but the type is parameterized by the distance unit that it is. So now when we add two distances, we can just make sure that a is the same all the way down, and then we can add two distances that have equal units. And this is great. Unfortunately, this doesn't solve the conversion problem either, but it does make the conversion problem a little bit easier. So now we can write these functions, which have quite a bit more description, or it's a bit more descriptive with what we're actually doing. You know, given some distance in miles, and then we can return a value of distance in kilometers. So this is our conversion function, miles to kilometers. And note how in the types we can see this transition happening. We don't have to like think about the value level, right? So likewise, we can define kilometers to miles in a very similar way.
When we declare something with a phantom type, do we need to give it a type annotation so that it knows, or like how does it know?
Yeah, so in the previous one, you don't, because you just say like the A's are the same. You know, we can add distance values that where the types are the same. So for instance,
if I'm creating a p-distance on the value
yeah. Yes, you do have to provide a type signature to tell the compiler.
And if you don't,
depending on the way you use it, it will infer the type. So if it knows you have some value and you do add distance and you never assign a type to one of them, if it knows that that A will be the same as whatever other distance value parameterized. It'll like unify.
Be careful to type annotate it, because if you don't, and one's supposed to be kilometers, then you add that
Right.
and infer that it's
Right.
miles.
Yeah.
Okay.
Should you also have a kind annotation to say that the A has to be a distance unit?
We're getting there. Yeah. Yep.
Previous slide.
Sure.
And this may be a bad idea. I'm going to a lot of this. But is there would there be any advantage to having add p distances go from p distance A to p distance B to p distance C? Build the conversion right into that?
Maybe, but that would make use of type families. Yeah, and so we're not there yet. So that would be, that is a way you could do it, but it requires a little bit more advanced, more language extensions. But yeah, you could do that. So then we can come up with this conversion function, this conversion type class, which we could have done, arguably in the beginning, but it would have to be over more granular distance unit values. But now we can just write the conversion function over distance, like the distance value itself, or the distance type itself. So we convert p distance A to p distance B, and we just have instances for the conversion from miles to kilometers. And we could just replace the miles to kilometers or kilometers to miles with the implementation that we mentioned in the previous slide, but let's just reuse it. And here is where we have to use multi-param type classes, because in order for GHC to accept that pconvert takes a type A and B, we have to put on that language extension. So that's not really that, great. We still had to add this type class where we kind of made these conversion functions, but what if all of this stuff could kind of happen a little bit even just a little bit easier, right? And so that's where we can kind of enter with generalized algebraic data types. The pragma that we'll be using is language GADTs, and that stands for generalized algebraic data types. So we mentioned before how Haskell, the kind of the cornerstone of programming in Haskell is algebraic data types. Well, these are algebraic data types, but generalized over the return type. And if that doesn't make sense now, it will when we're done talking about them. So in algebraic data type syntax, we have either AB, and we can easily convert this to GADT syntax, where we have two type parameters A and B, where the left constructor is a function from A to either AB. And this is the same as on the left. So whenever we use regular ADT syntax, left A, the constructor, we all know it gets turned into a function that takes a value of type A and returns a value of type either AB. So we can embed type information for data constructor return types. And you don't see it here, but notice how the return type of left and right are either AB. So what GADTs let us do is they let us play with these return types. We generalize over the return types of the constructor. It's no longer, the A and B for this on the left side is fixed. You can't change the A and B of the return type. Left A is always going to return either AB, and right B is always going to return either AB. But we could do some more sophisticated, munging of the types so that the return types of the constructors could differ. And if you can't see it yet, we'll still get there. This is just the introduction. So constructor return types can differ, as I just said. And finally, this won't make sense yet, but it's good to state it, that pattern matching on GADT constructors can determine the return type of the function case expression. So as we destruct algebraic data types, we use the case expression in Haskell. GADTs let us, when we pattern match on these constructors, they can inform the return type of the function, just as the constructor can inform the return type of the data type itself. That type information can propagate. And we'll show some examples, and this will all make sense. So we're going to translate this phantom distance type into generalized distance type, where the distance is parameterized over A.
Oh, can you go back?
Yep.
What's happening?
So we're just converting. So we're saying this is the phantom type representation, and then this is the generalized algebraic data type representation. So I'm just creating a new distance type with G. It stands for generalized distance. And this is even the same as the original distance value, distance type that was parameterized over or that had like a distance unit as a field. These are all kind of isomorphic. I'm just showing different ways to do them with these different techniques. So now with GADTs, we can parameterize this distance type over so we're going to introduce data miles, which means like we're going to define a type called miles, and we're going to define a type called kilometers. And then we can define a type class, gconvert, over A and B, where, and all this is very similar to the phantom type definition. So we haven't really utilized the power of generalized algebraic data types yet. This is just a description of syntax. So this is just a syntactic transformation. I'm not demonstrating anything more novel than the phantom types. I'm just showing you that this is basically isomorphic to the previous phantom example.
Let's go to the previous slide really quickly.
Yeah.
So what was the change here, really? What just happened? We had a phantom type definition.
Right.
And the one that is using generalized types is different because...
Well, it's not. It's isomorphic. It's just a different syntax. So with the generalized algebraic data types, we're representing the same thing, basically, with... so now we don't have the p-distance value. Yeah. The reason I didn't use a record syntax for the generalized algebraic data type is because it's actually kind of even more confusing. So the syntactic overhead for the GADT, you can still do record fields in GADT constructors, but it's like just injects more curly braces and more arrows, and it's a bit confusing.
So wait, sorry, so the thing on the left-hand side, the G instance double, that's the part that you get from this extension?
Right. So the constructor takes an argument of type double and returns a g-distance a value of g-distance A. Just like the p-distance constructor takes a value of type double, since that's the field, and returns a value of p-distance A.
Okay.
Yeah.
We would still say that A is phantom in the GADT version?
Well, now since it's not phantom, because notice how the return type g distance a. We could say g distance anything. We could put int. So like we won't because we want to use a distance. We want to use miles or kilometers. But and this is just a syntactic introduction again to GADTs. Yeah.
So does that mean that for GADTs it doesn't have value constructors anymore? Explicitly.
It does have value. So this constructs a value. The g distance constructor constructs a value. Given a double, it returns a value.
Like in the ADT example, that's already a function from double to g distance a. So
Right. So this is just the syntactic transformation. We'll get into like how GADTs help us, and we'll just write
like
coming up.
ADT a is phantom and the GADT is not.
Right. And you can't really see it because this only has a single constructor. But if it had multiple constructors, that's why it wouldn't be phantom, because the different constructors in the generalized algebraic data type could differ in their return types. They're not all constrained to A at the return type.
Oh, okay.
Whereas this one, p distance A, every constructor you had would be constrained to have the same return type.
Because you can do more, that's why it's not phantom anymore.
Right. Yeah.
Last question. I understand this is just a different syntax, but I want to decipher it. So that the g distance on the second line
Is a constructor.
is the constructor.
Yeah. It's a constructor. Yeah.
And you could name that a different thing, it's just conventionally the same.
Right. Yeah. Since there's a unary constructor, it's named the same as the. Right.
So the point is that you can define your return type. That's the difference between the two.
Right. Yeah.
So when you want to define different return type for each constructor that you might define.
Right. Exactly.
And we just don't see it yet.
Yeah, it's like in 2 or 3 slides, we'll see how this is like very useful. Okay. This is just a syntactic translation right now. Okay, this is just to show that we can do the same thing with GADTs that we did with the p distance. That we can do the g distance, what we did with p distance. So here's the motivation for generalized algebraic data types. So assume we want to have some expression language where we can either have values or like literals x, which can be true, false, or n. And I probably should have annotated it here, but let's just assume n is some like natural number. And then we can have expressions of the form e plus some other expression e prime. We can have expressions of the form e and some other expression. We can have e equals another expression, and we can have if some expression, then this expression, else that expression. And we can represent this as an algebraic data type with the regular algebraic data type where we have the lit. Lit corresponds to the x, and the expr corresponds to the expression. Does this make sense to everybody, how we've translated this kind of AST definition directly into algebraic data type? Cool. So we want to write our evaluation function. This sucks. This is only the EAD case, right? So this is entirely, and I'll walk through it with you guys. It's entirely too complicated because we have an EAD expression, should really only be able to add two values of two expressions of the integer type, right? But our ADT doesn't let us encode this. We can only encode that EAD takes two expressions. We can't enforce that it takes two int expressions. So we have to kind of evaluate E1. I'm looking at the EAD here. Evaluate E1, and then we have to say, like, if it's an int, then we evaluate E2. If that's an int, then we return the result. In every other case, we can't add those values. It's nonsense to say to add two E bools. Thus, in the case where the expression is an L bool, the literal is evaluated down to a Boolean expression, we can't add those. So we have to report an error every time. And here's the first exercise. So I want you guys to go to the file I mentioned. And it's a pretty quick exercise. I want you guys to implement the if case. Okay, so for the same function, you should see on line 46 of that file. It says exercise 1. Please implement the evaluation logic of the if expression. And if you don't learn anything in this workshop, let it be that like. Whenever you're representing an AST, and I'll show you, you have to go through the pain of implementing the if case. You don't have to if you think it's easy, but, and arguably it is a little easy, but it's quite annoying. And I'll go ahead and give you guys like, let's say 3 minutes. And feel free to talk amongst yourselves too, like if you need help.
Yeah, the do.
What did that? Did you do stack setup first? So you
So things that takes expression.
What stack
and
routine
routine
is
that
use this stuff?
how we get
If you want that as a word.
so
Yeah, you should be good members. It's not
so we want C using like condition using right
yes.
and we need to do a case.
So what's that word?
On the cons. Do we allow this one? That's like this is a do you get errors from that's the simple is true. That's not example of but it's case so now it's
fairly old.
but we know it's very old.
That's like
That's very case. That's what it is.
pretty sure. If you just use like stack upgrade to
What we need to do is cases. This does. You would need to check it's a board.
Just a heads up, if anybody has an old version of Stack, it might fail on the volatile. So do it as Stack
Yes.
upgrade.
Yeah.
Like if you have like 1.6 or 1.7.
Thanks for that. Yeah.
Then we have to.
Evaluating, but you're assuming it's going to end up being an E-lits, but it could be like any of these two. I don't see those cases as being in.
No, so evaluation returns an elit.
Oh, always. Okay. So
Yeah. So yeah, when we evaluate expressions, they go down to literables.
Are integers true here?
I don't know what that means.
I mean, we get to decide.
Yeah, I guess you're right.
No. Well, let's just choose.
I'm gonna like -3 true and everything else is false.
yeah, just keep writing.
Oh wait, elbow. It wasn't that bad?
Now it's just eliminating past the
Why do I have to happen much again?
Huh? Because so the type signature of eval is it returns a lit. It returns a lit. So an elit is either a bool or an int. Yeah, just if. I mean, you can do and if you want to. But this is not really the core. All right, guys, so I'm going to kind of continue now. It's okay if you didn't get it. I know it's kind of, the point is that this really is annoying, okay? I'm not showing you the answer, just know that it's annoying. That's not really the point of it. The point is for you to kind of like see how the types don't really help us here. We still have to kind of like evaluating these expressions could either return like a boolean or a integer, and every time we have to check whether it's a boolean or an integer, and if it's not the one that we want, we have to kind of say that we can't do whatever, have to return an error, and this is really annoying. So we can say, all right, well, let's try with phantom types, right? So let's say that now we can annotate the expression type in this ADT. It's kind of an exact copy of the previous ADT, except now pexpr is always parameterized by the type that it should be, right? So now you can see that the add expression takes an expr of type int, and two exprs of type int, and the and takes two exprs of type bool, and the if you were just trying to do, well, it takes an expression of type bool, and then two expressions that are of the same return type. So the parameter a, because the branches of the if then else should be the same type in order for the entire expression to return.
Unless you're doing dependent.
That's not actually required by the AST.
Yeah.
Right. Yeah, right. So that's what I was envisioning when I was describing the, yeah, right. I just showed you the AST, I didn't show you the types of the little expression language we're dealing with here. But so in the end, this doesn't help us because the phantom type can't inform the result of the expression. Every case that we implement must have the same return type, right? The px per definition only parameterizes A. It parameterizes A over all of the constructors. So we can't return a different type from this function because every single branch must have the same return type. The A can't inform the result because if add returned an integer and returned a Boolean, then Haskell would say, your return types in your case branches don't match, and this is not something we want. So that didn't help us, This evaluating this, we can even still construct values where this doesn't make sense. Neither of these fail. So the example 1, we construct it and we say true and false, and this should work. But the second one shouldn't really work, right? The equality type, if we go back, the equality expression should have x per A. But we can still construct a value here, and we'll fail with evaluation. So the point of this is that it didn't really give us anything by giving a phantom type, because we couldn't inform the return type of the function. So this is where GADTs come in. And now we'll translate our generalized algebraic data type to kind of use the full power of GADTs, where now our GLIT, our literal expressions, the x that we saw in the expression definition, is of return type bool, and the int is of return type int. Okay, so now we are saying that whenever we have a gint literal, its type is int. We carry on this extra type information to say that this is actually an integer underneath. And likewise with the gexpr, we can say that if the if constructor takes an expression of type bool and two expressions of type A, and then returns one of those expressions. And this is here why the A's have to be the same, because if it was A or B, we would have to have some extra sum type infrastructure, and that's kind of beyond the scope of this talk. So the return type of the gexpr constructors can depend on the type of the constructor fields. And this is huge. In the previous solution, the return type of all of these constructors were px per A, where A is kind of like unknown. But now in the generalized algebraic data type version, we know the return type of each of these expressions.
Can you go back for a minute, just to that slide that was the phantom types? So you're saying, oh, I see.
Yep.
That removes the need of all the error handling before.
Well, we'll see.
Right.
So now I want you guys to go back to the same file and do exercise 2A and 2B. And I really think that that you'll be, yeah. So yeah, for 2A, I want you guys to implement the gexpr AST that describes the code if true and false, then 7 plus 2, else 1 equals 1. So it should be on line 144. And I just want you to build a value.
You want us to build a value that represents
this expression. So for instance, you might use the gif constructor. And I'm going to do it along with you guys, so this time there's actually going to be a solution.
This is exercise 2A.
Yeah, 2A. Shh. I'm kidding. Exactly. No. So, I mean, somebody already said it, which is fine. But if you do this, you'll realize that you actually can't do it because the types restrict you.
So you are getting a little bit random because the compiler is telling you.
Yeah. So now we just actually can't construct these values by definition. We cannot manifest a value that does not have the types, the return types. So the problem comes here with gif. So the expression I told you to implement, these two expressions differ by return type. The equality is doing equality over integers. But it doesn't matter. But it returns Boolean. But the other expression, 7 plus 2, must be int as a return type. So this is actually, not doable. And this is what we want from our algebraic data types. It would be wonderful if we had a framework where we couldn't construct values that are, shouldn't be able to be represented. So please move on if you're done to exercise 2b. And this is going to be the conclusion of the GADTs, because really exercise 2b kind of shows you the full power of generalized algebraic data types. Our evaluation function becomes beautiful, for lack of a better term. Yeah, and please feel free if things are not compiling in this file. One thing I would recommend, I will show you my screen. So one thing I would recommend is to kind of have this GHCI open. So what I've done is I've just done stack GHCI on the file. And what this does is it compiles the file. And then every time I make some changes, I could just do R:R. And this is going to reload the file. So then if I'm going to make this be something that does make sense. And to get rid of my type error. Notice how it should accept that. Couldn't match type A with, oh, right. And so the reason I had to put an A here is because before, we couldn't decide on a type. So now we know that it's going to be int. And right, I actually have to have like a redundant glit here. That's annoying. This is why people write parsers, so that you can quickly test your expression language without having to do this endless sea of parentheses.
I have a question regarding the exercise. So if I change the value so that both elements of that analysis return an integer always,
yeah,
it still doesn't compile because it's saying the value is gx of int, and it was expecting gx of a, where a is anything.
Let me see.
Like the only thing that I changed was that instead of like I return an int and an int,
yeah,
right? So that gives me.
But there's no, so you have to do that add here. You haven't done gadd.
Oh, I'm not adding. I just said like 7 and 7, right? I made this into if true or false, then 7 else 7. That's basically my.
Oh, okay, sure,
right
sure, yeah.
And now it's still complaining that.
I think it's a parens mismatch.
But he's saying that because.
Oh yeah, no, that type. Yeah, and I had to do that because the types were different before. But now you should change it to int. Yeah, you should change it to int. Yeah, and that's what I just did here. So I did expr int.
Oh, sorry.
Wow.
So I have a quick question because I follow everything you're saying right now, but I just don't understand which part wouldn't be allowed in normal ADT in Haskell.
So we don't want to be able to construct an expression that doesn't make sense.
Yeah, but which part of the syntax would not compile without the
No,
extension?
it would compile. This, if you implemented this in the original ADT that we gave, it would compile. So we would be able to construct this kind of like nonsensical algebraic data type. But now the GADTs don't allow us to do that. So has everybody moved on to the 2B? Yeah? Cool. So I'm going to switch this back over.
So what stack command are you running on the right-hand pane right now?
It's just stack GHCI on the file itself, because there's some files that also have type errors that we're going to get to and do exercises. So it's stack GHCI on the file that I'm using. Yeah, in hindsight, I would have had much better resources for you guys to kind of like set up this feedback loop. But up until this morning, I was kind of being very anal about the last hour's content. So since this is a little tough, I'm going to give you guys 3 minutes from now. I know we kind of got to move a little. Even if you just get a few of the cases done, it will kind of cement in the final. I have the solution up here, and I can help you out. We got 3 minutes. What's going on?
Yeah. So the comment to the south side is what I'm making.
Sure.
In the original one, one of the cases is elit,
right,
and it has an elit.
Yeah.
And these are different.
Yeah, because elit here is a constructor,
right, one is a type
and the other is a
constructor,
type.
one's a data constructor.
Yeah.
Right. So then this is a pretty easy case.
Yeah.
In that you just literally are like scoop it out. Because it can pass back a literal.
Right. Yeah.
Whereas here our thing gives us back an A.
Right.
So
because now the underlying value, we no longer have to like think about just literals in our values. The underlying literals are like either a boolean or an int. So DCL bool. So we can just return those when we fully evaluate our gexpr.
Yeah.
It will go to a glit, and we can just extract the bool or the int.
Okay. So then in that case, this is gives us a g. So am I starting right? I still need to do a case on the expression.
Yeah, so that's why I gave you eval lit. So this will just evaluate the lit. Yeah, so we just like unpack that, and so yeah, you'd write like gval.
Like that cute.
Yeah, and that would be the correct, but it says geolit instead. Yeah.
Okay, I see.
And that just goes from a glit A to okay.
I think I got it completely. So like with typical normal ADT, when I construct, this is a type constructor, right?
Right.
So like the type constructor could be of this constructor of int of whatever, and I don't take control over
the return type of each.
But with GIDTs, I can actually say, well, you might be constructing of A, but whatever. But I will give you here with this constructor, it's always going to be of int, right?
Right. I can only accept gexprs of int. Yeah. And then notably, I can only return gexprs.
Yeah, sorry, return. Yeah. Right? So whatever you construct with this value constructor, it's going to give you a value, but of type gexpr of int, not of whatever's. Okay, makes sense. Yeah.
And now we know because we've just pulled out the G, we know that
But it's not a question, it's a comment.
Sure.
Very much. So I think like each time we have an either or any type of an exception non-termination, the type is kind of poor. Okay, it's not a true proposition. And what we have done is like we now don't have an exception grade.
Yeah.
We have a true proposition. So it's like
yeah. Notably, we just can't construct values or expression trees that don't evaluate properly. Yeah, exactly. Right.
When we do the pattern matching on the case expression, we get two expressions, right? Because I can read this as
two expressions of type int.
The constructor with the two things. Okay. Right. I kept like looking at it, I was like, but it evaluates, do I only have one of these? Something about the function.
Oh, you know what we can do? Yeah. So we're gonna
we get these,
we're gonna
and
return.
these are G expressions.
Yeah, so we're gonna
of type
return
int. Oh, we literally just
gval lit plus gval lit, right?
Yeah.
Oh yeah, gval. Yeah, just gval plus gval. Oh shit.
Yeah. Well, gval.
It takes your expression. We have an expression A, and this gives us a thing. So if we have a G expression in, it'll give us an int out, which means we can just add them.
Yeah. So gval. Yeah.
All right, guys, I'm gonna give you like 30 more seconds.
Oh, this is really easy. Oh, look at this, just break.
That's the point, right? We've defined our types, and now like the.
This makes sense.
Yeah. Because now you try to pass it, it will
We did not have to.
Yeah.
Right. Oh, sorry, that's an old comment. My bad. I ended up not doing that. Yeah, yeah. I built it in. Oh, that's the equality constraint you see? Yeah.
Oh, that's so nice.
Yeah, I was like, maybe they can figure out that they have to. All right, guys, so I'm going to give you the solution now. So one thing I did want to point out before I started the solution is this constraint here on the G equality constructor. So this is another thing that GADTs let us do. And we can do this also with algebraic data types, but it's a little bit more kind of frustrating. You have to use something called existential quantification, and you can only do it, I think if I recall, with unary constructors. If you have more than one constructor, then you can't constrain the type. So we also force that you can't construct an equality expression unless the underlying A's have inequality, an instance of the EQ type class. So without further ado, the solution is, well, so I already gave you the G eval lit, and hopefully you guys saw that there and used that to help. So this is our evaluator now. You cannot implement this a different way. So because of the way we've specified our types in the GADTs, you cannot come up with a different solution. And sure, you can syntactically come up with a different solution, like maybe you're formatted differently. But ultimately, the semantics of this function, there's only one implementation of it. And this is a beautiful expression of how by putting a little bit more work into understanding, this thing here, we really gain the power of expressing exactly what we want on the value level, such that there's not even another way to implement this expression.
Do you have like a real world example of where GADTs used to create a library or something?
Oh man, I would. If they were rarer, I probably would, but they're everywhere. Anything in the Haskell domain, any widely used library that's, let's say, just 2 years old, I guarantee you somewhere in that code base there's a GADT. But yeah, sorry, I don't have a concrete example.
I have a question. In the G-add E1,
Yeah.
you pass E1 to G-eval,
Right.
but please accept G-alert. I mean, it should be G-expression. E1 is G-expression of int.
So say that one more time.
Like E1, according to the definition, is G-expression, not G-alert.
Right, which is why I do G eval. I recurse on the eval, not the eval lit. So only the lit is evaluated with, yeah. And so, yeah. All right, so I think you guys have been here. If you guys want a break, should I give, does everybody want like a 5-minute break? And then we'll do the second half?
Yeah.
Yeah? A break? All right, so because it was half and half, well, I think it's okay. I think it's okay to give you guys a break. The next section, it gets a bit. Oh man, we're not even gonna get to the third section.
No break.
No break.
All right. Overruled. Okay.
Do you need a break?
I don't think so. I'm feeling all right. Feeling all right. Okay, I'll go slow. So now we're going to get into actual type level programming in Haskell. Believe it or not, you haven't really done type level programming yet. You've used types in Haskell to constrain the way you can implement your functions, but unfortunately, we haven't really gotten there yet. We haven't really gotten to type level programming. So what I'm going to talk about in this section are type level functions, value and type promotion to the type and kind level, and finally higher kind of data, which just means they are data types that are parameterized by types that are a different kind than the usual kinds that I've introduced yet. And I know none of that makes any sense, but it will make sense in a little bit, hopefully. So I don't know why that faded in. So we've already covered the GADTs, kind signatures, and multi-parameter type classes, but in this section we're also going to talk about data kinds, polykinds, type families, type operators, and just sprinkle a little bit of undecidable instances in there, which we'll get to. So I don't expect you to read this, But if you Google for type families and you go to the GHC wiki, you're going to see this, which is, well, I'll read it to you. It says, the concept of a type family comes from type theory. An index type family in type theory is a partial function at the type level. Applying the function to parameters, called type indices, yields a type. Type families permit a program to compute what data constructors it will operate on, rather than having them fixed statically, as with simple type systems, or Haskell without the type families language extension on. Or treated as opaque unknowns with parametrically polymorphic types. This is not a great explanation. I put it up here because I think it's confusing. All you need to know is that type families are type level functions. They are functions over types. You define some function that takes 2 types as an argument, or n types as an argument, and returns a type that is evaluated at compile time. So it's a way of abstracting over types if you don't want the types of your functions to be fixed statically. So for an example, we have value level functions like const, which takes 2 values, a and b, and it just ignores the second one, right? But we can do the same thing as in a type level function, where we have a type family const, which takes 2 types, a and b, and it just returns the first type. So if you evaluate this type constructor, const ab, or this type family rather, it will just evaluate to the first type that you applied to it. So you can see here an example. If we do const 42 of Haskell, we get 42 back. And in the example there, we first have to tell GHCI that we want to use type families. And then there's this nifty little kind of command that you can give GHC that's kind exclamation point. It's different than kind. It's different than colon kind or colon k in the sense that it will evaluate the type. It will try to reduce the type into its kind of, the smallest form it can. If you do not put the exclamation point, it'll just say const int char equals constant list of characters. So that's why we do the kind exclamation point. And this is very good when just as you use the REPL to GHCI to debug your value level functions, when you're playing around with type families and everything compiles, but you're not sure it works correctly, you go over to GHCI again, and you do the kind exclamation point on all of your type families that you want to evaluate and test. So as I mentioned before, type families are evaluated at compile time during type checking. The domain is types and the codomain is types. Just like value level functions, the domain are values, and the codomain, which is basically the range, or the result is a value. So in type families, domain is types, codomain is types. These cannot be partially applied. And I have a little star here because this bites us if we want to do kind of sophisticated things in type families. And unfortunately, I do have an entire talk dedicated to how we can get around this. But it first requires you to understand basic type level programming and type families in general, and the limitations of type families and why they can't be partially applied, which is just kind of beyond the scope of this talk. And finally, denoted with type variables and kind signatures. Just as in this example, the arguments to const are denoted with variables like x and x. And then we have a type signature. In type families, we have type variables a and b, and we have a kind signature, which is, in this case, const is just star to star to star. So this is a very confusing slide, but I thought I'd throw it in there to just demonstrate that type families cannot be partially applied. This dconst is a data constructor that kind of acts similar to the type family const. And you can see here, we introduce a type family called curry dconst, which means like partially apply it, which takes some type A and returns a kind of star to star. So you can see, given an int, curry dconst int, we return dconst int. But remember, dconst has to have 2 type parameters before it's a value, so thus it's still of kind star to star. But if we do that with type families instead of a data constructor, and we try to write the same type signature, hopefully you can see the pattern here. It's not like a whole lot of different code, just the different names. Then we get this error that says on line 15, tconst should have 2 arguments, but it's been given 1. So I'm just demonstrating, all you need to understand here is this means that we cannot partially apply type level functions. We must fully apply type level functions when we use type families, which is a bit frustrating. And again, I have an entire talk dedicated to explaining this, but it's beyond the scope of the workshop. Type level functions is going to fade in every time. I duplicated these slides and forgot to change that. So ultimately, GHC's kind language is limited. As I mentioned in the beginning of the talk, there's star to star for type constructors. There's star to star to star. There's type constructors that take, star to star, maybe a functor type thing, and then return a type kind star. It's all stars all the way down. But it would be really nice if this didn't limit us, Yeah. Yeah, and we'll get into that. Yeah, we're getting there. But that's with the language extension. So that's kind of like what I'm building up to. With only these language extensions that I've told you so far, not in the beginning of this section, but the ones that I've put at the top of the slides, we can't talk about any more complex kinds yet. So for an example, if we want to declare the type true, we have to do this. If we want to declare the type false, we want to do this. And then we can implement the OR type family, which is basically a type level Boolean OR, where we say if we have OR of the type true in anything, then we give true. If we have OR of something and true, then it's true. But if we have OR of the types false and false, then this is the case that it's false. So unfortunately, OR can be instantiated with any type of kind star. And I say unfortunately, because we'll see in this slide. That's how we've specified it using the kind signatures. But note how any is in italics. So OR can be instantiated with any type of kind star. And it can return any type of kind star. So we can implement a case in this type level function where we have OR of int and character and return the type maybe IO bool. And if that doesn't make any sense, that's because it doesn't make any sense.
But it is possible.
But it is possible, right? So without a more rich kind language, we basically have untyped type level programming here. Note how, for the types of true and false, I can declare something insensible, but I can just pass it whatever type and declare something nonsensical. So this is basically like untyped type level programming. Yeah. So enter data kinds. Data kinds is kind of like the first extension you'll encounter that's going to kind of be really confusing, because talking about values and types in the Haskell domain is pretty difficult on its own coming from other languages. But now we're going to talk about types and kinds, and we're going to be programming kind of entirely in the domain of types and kinds. So what data kinds does is it lifts values to the type level, and it lifts types to the value level. So when we declare data bool, imagine prelude's not included, so we don't already have this declared. This ADT, it seems like, really declares the kind bool and the type constructors true and false. It also, in addition to it, also declares the type bool and the values true and false, but it also declares the kind bool and the types true and false. So now, using kind signatures, we can write a type level function where the two arguments must be of kind bool. And the type family must return a type of kind bool. You can see the implementation is the same, except for these little ticks in front of these. And these are not necessary, but they visually denote the difference between the value and the type true and the value true. So whenever there's a tick in front of it, it means we're talking about the type true. But if there's not, we could be talking about the type or value. And it's not necessary, but I tend to do it, especially for this workshop, just to denote that I'm talking about the type true and the type false, not the value true and the value false. This is a type level function, not a value level function. Question?
Is there any way to define a kind without data kinds? Like define a kind
No. So that's the language extension that allows you to extend the kind of the kinds system in Haskell. Notably, you do not have to declare them all yourself. When you turn on data kinds, every ADT in scope will get lifted. So if you've imported Prelude and you define data kinds, you do not have to redefine bool. Like, you just have the kind bool and the types true and false.
In practice, wouldn't this be hard to maintain normal Haskell-like programming and programming like this? Wouldn't we get confused a little?
And that's what the ticks are for, and that's the best we got. Yeah, so the little backticks.
When you activate this extension, it automatically creates a type value for your constructor. So
I think the language is a little bit confusing, but it lifts all values to the types. Like, so now you can use all values that are in scope as types, and you can use all types as kinds.
Did it declare this tick convention for you automatically?
Yeah, this is something GHC. Well, it's something DataKinds does, is it lifts the syntax.
Oh, okay, so you didn't.
No.
And does it do that for all your union types?
Yeah, it just does it automatically for everything in scope. It will lift everything.
Int instead.
Yep. So now you have int is a kind.
So do you have like tick 1, tick 2?
We'll get to that. There's some implementation details, and yeah, what was that?
Do the kinds have to be fully instantiated using the type of
No, but so we'll get to that. There's higher kinded type families, and I'll talk about that in later. Question?
Yeah, I'm just curious the extent to which sort of the Haskell or the prelude had been encoded in sort of type level programming.
Yeah.
If you're doing sort of the base values here,
Right.
Imagine doing it for
Yeah, the base values, again, are just kind of more for demonstration purposes, so I can annotate them. Everything's lifted. If you've imported Prelude, you don't have to. Yeah. So all of the ADTs in there are lifted automatically. Yeah. So I don't know if you guys agree, but now we have typed type level programming, and this is great because now we cannot instantiate type families with kind of nonsense values. So if you would open up the file, and sorry about this, I should have done this ahead of time. I want you guys to open up the file source type level / basics exercises basics.hs. Sorry about that. And then if you could do, yeah, that's inside. I'll just leave it up here for a few seconds. And so if you could do exercise, hold on, yeah. Yes, 1 and 2. So exercises 1 and 2 in that file that I.
Could you just maybe show that previous slide?
Yeah.
So we have like a reference.
Definitely.
It's right above it. Oh, okay. So
Yeah, right.
Is there a way to get inexhaustive case matches for?
Yeah, but it gets significantly more difficult as you try to encode all of the kind of value level programming constructs that we have.
So are we fixing kind signature as well, right? Because the and doesn't have a kind signature.
If you want to. So I mentioned that it will infer the kind. So GHC has kind inference. And what this means is if you define your closed type, if you define your type family over the kind, it will know that.
But if you end up using, like, for and, we can say everything else is false, everything else is true, right?
Yeah.
So that would be kind of.
Yeah, it would. Yeah, as an exercise, why don't you guys define the kind signatures? I think maybe I reorganized some stuff, so that's why I didn't know if I was going to introduce data kinds yet. Yeah, so the and, so exercise 1 is implementing the and kind type family. And it would be beneficial if you guys annotated the types. You don't have to if you use the ticks with true and false.
Is our type system Turing complete yet?
Is it Turing complete yet? Yes. Well, if you have on undecidable instances, yes. Because that's partly, and we'll get to it, but that's partly what undecidable instances does, is it says, I'm not going to check if your type family applications terminate. I'm just going to let you loop in forever. And so that's where compilation is not guaranteed to terminate.
Okay. That's good.
And exercise 2 is a little bit, it's getting interesting now. Exercise 2 is implementing a conditional expression as a type family. And if you would, it'd probably be best to annotate the kind signatures there. Although there is a later exercise that has you, if you don't implement the kind signatures, maybe you'll figure it out now and you'll run into that problem. I'll have to address it now. But later on when I introduce polykinds,
function of values.
Mhm.
So, and there are lists, right?
So all algebraic data types, so not all values, right? So float is not an algebraic data type, yeah. Mhm.
Yes, I have a type level function, or like, how can I evaluate it?
Right. So I actually have some tests written, and if you don't understand the test, that's fine, because it's kind of stuff that we would cover in the third section that we're probably not going to get to. But ideally, you open up a GHCI session and keep compiling, and you should have a type error. You should have a type error right now for if then else. But then if you implement it correctly, you'll see no type error.
What's the precedence between the has type double colon and the tilde character? Like in lines 53 to 50. Well,
So that's
like is the parentheses around the and to the end, or
it's beyond the scope of what we're talking about right now. It's a way I can prove that you guys have implemented the type level function correctly.
Okay. What is that also? The colon tilde colon?
It's a constructor. It's a type constructor.
Okay.
Yeah. That just lets me construct a type that may fail if you guys don't implement and correctly. Yeah, sorry.
I see that with the if then else family, like I guess normally it's written like this.
Yeah.
But this sort of limits the conditional to something that's already evaluated to like either true or false. Could you generalize it to sort of a type that would take another type and then evaluate to, I don't know, like bool or something like that?
So without
take the A as an argument?
Yeah,
Or something, you know
yeah.
what I'm
So
saying?
that's called like a higher kinded type family, where you like your kinds are not. Well, you have kind level functions, kind of. Yeah, yeah. So well, no, it's the type level function as an argument, right? So it's not kind level function. Sorry. But yeah, you can do that, but there is like there's a few caveats that, you know, type errors get really confusing.
Sure.
Yep.
So this if and else, it has to return the same kind, right?
Yeah.
But it can return different types in that kind.
Yes.
That's kind of blowing my mind right now.
Mhm.
Like,
Yeah, exactly.
So I put a kind annotation on the if then else, and I assume I can only put it on the condition, right? I can't put any annotations.
You can put an annotation on the, and so that's actually like exercise 4 or something.
Okay.
Yeah,
I'll
it gets,
wait.
yeah. All right, so I'm gonna.
But here's where I find it interesting, is that in that if then else statement, I will return either A type or B type.
In the if then else, it's not type. Yeah, you can return the A type or the B type, which have to be of the same kind.
They have to be of the same
Kind.
design. So how do I annotate that?
We'll see. So yeah, the next step is that. So let's just have a.
But the compiler does that. So if I try to call it with different kinds, it would freak out.
Right. If you try to return different kinds, yeah. So if you've annotated the kind signature incorrectly, then yeah, it would. So I'm going to go ahead and switch over to this screen. Okay, and I'm going to implement the and for you guys. So notice how I have some type errors over here, which is, let's go all the way down. There we go. My type errors at the very start is molt. Here we go, if. So my if then else is wrong, right? Because I haven't implemented it. So that's natural. I have these little, if you're curious about these tests if then else, unfortunately we're not going to get to it today, but seeing how much I covered today, I'm happy to come back next year and give another talk, where we actually do the second half of this whole workshop. So one thing you might want to do is implement this kind signature. What am I doing? It's so hard to type like this. Where we have kind bool, right? And then we just care that A and B are the same kind. So we say if true, A, and then if, then, I don't know what I'm doing this. I actually have a solutions directory where you can see all of the solutions, but I didn't want to give anything away. So you can see I have this type error here, and that's what the test if then else lets me do, is I can check, I can say that, I'm not going to get into it. Just know that if you've implemented it incorrectly, the type error on line 67 and 68 won't go away. But now I have, let's say, did I record, did I write? Now when I scroll up, we probably won't see the type error, I think. Yeah, so no longer on line 67. That's great. All right. Hopefully everybody followed that. We have 30 minutes left of the workshop. We might be able to get a little bit into type level lists in a bit, but we will see. There we go. Yeah.
So this if then else is not a shortcut, right? There's not a lazy behavior here. Right?
No, but first-class families or first-class type families, which allow you to partially apply type families and move them all around, which again I won't get to this time. You can implement lazy evaluation. So type families are strict by default, but you can encode type families in a different way that let you kind of have lazy type level programming. Yeah. So this is a big slide. I just wanted to say that now we're going to do type level natural numbers. It's still in the realm of data kinds. There's something called the Peano Axioms, which is the way we can talk about numbers. Really, you don't have to read them all or understand them all. What we're really interested in is the fact that 0 is a natural number, and that for every natural number n, the successor of n is also a natural number, right? So this is a kind of a inductive way to describe natural numbers, where we have our base case 0. 0 is a natural number, and for every successor of a natural number, that is a natural number as well. So we can declare the kind nat, and the type constructor is 0 in successor. So you can see that this is an inductive definition. Unlike the true and the false, the successor of nat references the nat kind. So we're defining, again, the type 0 and the type constructor successor, which takes another nat as a type before it's fully instantiated and before we actually have like a type of kind nat. So we can add type level natural numbers here. We can say that if we add 0 to m, the result is m. And if we add the successor of n to m, that is the same as saying the successor of adding n and m. So basically, we're just shifting successor to the outside and adding n and m. And if you note, this will recurse. This is always making the successor of n smaller. This is also always making the first argument to this type family smaller until n hits the base case 0. And then, so basically, you can think of it as applying n successors to the head of the m natural number. And the reason I didn't go into detail here is because I have a computer science degree, and unfortunately, we were taught this, but I'm sure this might be a little confusing. But this is kind of like a canonical way in computing to represent natural numbers. So sorry if it's a little bit confusing. Just know that this is the way it's canonically implemented, adding to natural numbers. So that's all I'm going to give you guys for exercise 3 and 4. I feel like you guys are going strong. You're getting it. Yeah.
If you wanted another type family that added other things besides natural numbers, can you define it with the same name, or does it have to be type?
It would have to be a different name because you've given the kind signature nat, and you've kind of restricted it. Yeah, so if you will implement exercise 3 is the type level multiplication of natural numbers, which might be a little tricky. And then the exercise 4 is the type level exponentiation of type level natural numbers. So we don't have a ton of time. So I'm going to give you guys 4 minutes here. And I know it's fast, but I will implement the solutions myself during those 4 minutes. And then I will quickly go over them. Unfortunately, these type families it forced you to kind of understand the logic behind Peano numerals, like how might we compose these two constructors and the successor and 0? How do we put these things together to end up with a natural number? And if you do it wrong, you might see some really wicked type errors on line 98 through 100. It's pretty fun. If you implement it correctly the first time, I encourage you to implement it incorrectly, and then it will display something funny. Yeah, that's at the bottom. That's kind of like a type alias.
Oh, I see.
Where 1 is just the successor of 0. Yeah.
is there any requirements, like what you have there, you've got n and m the annotation, and then n and m below, you identify that?
Yeah, it's no requirement there. I just did that. You know, it's kind of, I'm torn between whether that's more intuitive or less intuitive, that the types and the kinds and the type arguments in the type family and the arguments itself are the same. No. Because ultimately this is pattern matching. This is just pattern matching on a type.
Right.
So now, at this point, so at this point, yeah, sorry. So this is actually
exhaustive case management.
This is actually.
No, you just have to. Is that a warning, or is it an error?
So we don't have to.
I'm not getting either.
Oh. So I think, if I'm not mistaken, I think GHC recognizes that we're always recursing, that we're always making the first one smaller, so that it knows that we've covered all cases. But if you've implemented it incorrectly.
So if I were to comment out that second line,
we're implementing.
No, this is.
Yeah, it might, but I'm not sure actually. It's a good question. Try it out.
We need to produce the type
I think your test cases suddenly fail.
We want to
Right.
iterate over
Right.
one of them until it's 0.
Right.
And then. So we maybe want to do the one case.
Okay. So what we can do is yeah, you're right. So we'll do.
So that it one.
Yeah.
Is the base.
So we'll do base case of
Can we use those types of changes?
Base case of y is y. And then so tax 1 equals mod x. So
how do you get a because you want to decrease it maybe?
That's what I'm thinking.
And then keep it
So
adding.
now we're going to do.
All right, guys, just 1 minute.
So now we're going to do
Yeah. You want like x minus 1. That's like a little. How would you do it?
No. So different.
Exactly different.
So I can just reuse add.
We can add it together over.
That's what I'm saying.
So, but we can do.
There's a caveat to that, but I'll point it out.
No, I know.
What's the other?
So you wanted to.
Oh, that's knowledge. Okay.
Oh, you just pack it up like this. You just do like this. Should we do this? Then you got this is now the decorate.
All right, guys, we have to move on in order to get to just a few more interesting things. I'm going to go ahead and kind of give you some caveats. Whoops, here we go. And say that if you don't, so some of you may have noticed that in the multiplication problem, well, you wouldn't have noticed it because I went ahead and did it on my own. But if I didn't turn on the undecidable instances type, language extension, then you would have gotten an error like this that says, basically, I cannot nest type family applications. Hopefully you realized you had to reuse add. But if you didn't, that's just, again, probably a function of whether or not you've been exposed to Peano numerals before or not. But you would have gotten this error. So unfortunately, we have to say, GHC, trust me here. It can't guarantee that we are reducing. So before in the add implementation, it understood that we were always reducing the first argument down to the base case. But here, since it won't follow the add type family, and so thus it won't guarantee that it doesn't know that we are going to terminate. So undecidable instances basically says that I can't guarantee that your type family terminates, which means if you turn on undecidable instances, you could write your type families such that your compilation doesn't terminate. And that is an unfortunate side effect of where we are today, but maybe somebody will change the type checker such that they follow the type family applications. I'm not entirely sure of the details why it doesn't work like that. So With more ergonomics, we can, I don't know if you saw in my tests, and oh, well, let me show you the answers. Sorry, forgot about that. There we go. So the answer for multiplication is, as you saw here, if we multiply anything by 0, it's 0. If we multiply by the successor of n and m, then we just add m and then multiply n and m. So basically, it's like n additions of m, which is the way multiplication is usually defined over numbers. And then I'll get into this next, type operators, but we can actually define infix operators that instead of mult, we can use like maybe a little bit more readable type family applications. And then
Never optimize your multiplication of the multiplication to also look for 0 and 1 on the right hand side. Like that.
Yeah, you can. Unfortunately, that once you start doing a little bit more complicated things, the simpler your type family definitions, like the less optimized they are, the less gnarly type errors you're gonna have to fight. That's an unfortunate consequence. I was fighting something for like 2 or 3 hours yesterday morning trying to prepare for like the next section, and it was because I had this extra case in my add type family where I was like pattern matching on 0 on the left and then pattern matching 0 on the right, and I just like couldn't prove something to the type checker. And the final case after 2 hours was that I just deleted that second pattern match and it worked.
Yeah. So tomorrow, shameless plug, tomorrow 1 p.m. So basically, if you do like a split, case split on the left-hand side in the class versus the right-hand side, that introduces different propositions in the type level.
Right.
And different things will type check, different things will not type check.
Right. It's really frustrating.
Well,
yeah. And so just without, I'm actually not going to cover the explanation. It's just, it's actually more of a Peano numerals, but just more of an exercise. So here, you see this here, it's probably not the best idea that, I think here to encode it, I have to do this, but I'm not sure. Now we are going back. So we can define type synonyms for type family applications. So if you could have seen in the tests that I use these numbers here. It's just a little bit more ergonomic, and then I can define them with previous type synonyms, because type synonyms are just synonyms. They just kind of like, it's like search and replace. 1 will be replaced by successor of 0. But this is still pretty annoying. So enter type operators. So we can actually define infix type operators at the type level. So just like I showed you in the file, we can define an infix multiplication. Just imagine this as being mult, but instead of mult, it's an infix operator. And you can define fixity, which tells the type system which type level operators to kind of bind together more tightly. And just for kind of to complete the whole story, there are 3 kinds of fixity: non-left and right associativity, and 10 precedence levels, 0 to 9. And then 9 binds most tightly, 0 binds least tightly, and if there's nothing, then it defaults to 9. So here our multiplication type family will be 9 fixity. And this is an implementation detail, and you can play around with this if you really care about understanding your big, long type family expressions, which nobody really usually ever has.
So why do you use the regular plus for the decorated star?
Because star is kind of like a reserved thing for kind. So whenever we use star in types, GHC wants to infer it as a kind star. So that's why I kind of put the colons in the multiplication. I think there's a way to get it to work, but you have to fiddle with like imports and stuff like that.
So it actually make the users clear, the uses of the code clearer actually if you put the colons around.
Right, yeah. If you had some way of denoting the type level function, yeah. Question?
Yeah, it's 0 times n equals 0. It's in the n times 0.
Yeah.
It's still valid.
Yeah, because if m is 0, it's just going to do 0 plus 0, 0, 0. And it's just going to be a whole chain of 0 plus 0 plus 0. Yeah. So with even more ergonomics, we can turn on both type errors, type operators, data kinds, and import GHC type nats. And they give us, they actually lifted all literals 0 through infinity, or whatever the max bound is for integers, to the type level. So now we can evaluate the expression 1 plus 1 That's not a type signature nat. That's a kind signature. 1 + 1 kind nat equals 2. These are all kinds, and we can do arithmetic at the type level, which is either really cool or really confusing. I'm not sure. Yeah. So it depends on the context, depends on the module you're writing. We'll use these type level natural numbers for the remainder of the workshop because this is a type level workshop. I'm not going to be demonstrating any integer expressions. So if you see something like this, just know it's at the type level.
Does that use colon, star, colon?
No, it just uses, right. So even in this module, it uses star, but that's what I couldn't get working. So there's some way you have to mess with the imports and the language extensions to get it to interpret it as. But they define a type family, star, for multiplication. Yeah. And so without going to the file, this exercise 5 is actually not going to be an exercise for you if you didn't annotate the kinds of if, then, else all the way. And I want to just kind of go back to that and display this up on the board and go to my version of if, then, else. And the problem is here, I've annotated A and B as kind star because maybe, I hadn't done this workshop and I'm like, I'm really familiar with kind star, so I know A and B have to be the same kind in order for this to work out, but I wasn't thinking of higher kindedness. So if I do this and reload, then it will get the type error that says on line 132 that this expression is wrong. So it will say this expression is wrong because in both cases of the if then else, so don't look at this squiggly colon, don't look at anything to the right of that, just see the if then else type family there. So I'm returning type level natural numbers, which have kind nat, not kind star. So I would get the error that says, I can just block that out, there we go. I'll get the error that says expected a type, but 3 + 2 has a kind nat. When it says a type, it means a type of kind star, because these are the types that can inhabit values. So the fix to that is something called polykines. So what I'll do here is introduce the fact that a lot of times we want our kinds to be kind polymorphic. Just as we want to write a type variable A in the type signature, we want to write maybe a kind variable K in the type signature. So GHC will automatically infer polymorphic kinds for unannotated kind signatures with polykines on. Thus, if you did not annotate your if, then else type family with star or some other thing, it will just infer the type kind, the polymorphic kind. But if you do annotate it, you have to have some type variable K or J or some letter that or some string of characters. But they must be the same because, again, if then else, the types that are computed must be of the same type. So we have 5 minutes left, it says. We don't have until 2, we don't have 15 minutes?
It's 11:50.
Yeah. Okay. All right, well, I definitely have 15 minutes left of talk. So if you guys want to leave in 5 minutes for lunch, because I think lunch is at, yeah. I'm happy to keep talking. But now we can get into more interesting things where this all becomes relevant. We all, okay, so we're doing all this type level arithmetic, but what does that get us? Why are we doing that? Is it just for fun, or do we actually get something out of it? And quickly, there was a question?
Yes, can we
Yep.
check that all these pattern matches are exhaustive somehow?
I am not sure. I think GHC will I think maybe not, but because the type family declarations, you're defining the type family. You're saying that this type, if these two types are arguments, this is the resulting type. So GHC doesn't know. It doesn't want to assert that you want to define. Maybe you want a type error in this other case. Maybe you don't want the type family to be defined over all of the type constructors. So I think it won't assert that you have to define those. So if you will let me, in the next 10 minutes, I will, and again, feel free to leave, but I want to, for those of you who want to stay, let's talk about length index list. I'm absolutely not going to make it all the way through. Yeah, extensible records is ridiculous. Okay, so hold on. Let me conclude now and say that was a really kind of wide, breadth introduction to type level programming, all the tools you kind of need, phantom types, GADTs, all the type extensions, how we can do type level arithmetic, how we can encode things like conditional expressions. And I will kind of let you guys all leave for like 1 minute if you want to leave. And then I'll like start again in like 1 minute, just so that there's not like a whole bunch of movement. Okay, so in the interest of time, I'm going to keep going and say we're going to talk about length index lists. So one thing that you know is that if you have a list and you want to access the 7th element and your list is 3 elements big, you're going to get a runtime error. That sucks. We don't like runtime errors in Haskell. We want to try to, because ultimately it's a side effect. You know, you might have a pure function that says like, hey, give me the 7th element of this list, but it might throw an exception. And that absolutely is not a pure behavior. So you've already seen all of the the kind signatures in green. We're going to add just a few more constraint kinds, which allow us to now give the kind constraint to our type families. Our type families can now return constraints, and we can use those type families in the constraints of our functions. And then flexible contexts and flexible instances. And this just lets us define specific type class instances in a little bit more general way than usual. There's not a whole lot interesting going on there. So, whoa. All right, we're going to do live coding. So because I actually stopped here. Yeah, I stopped kind of making slides in the interest of time, right? Because now the workshop's over. But you know, I didn't want to make like 50 slides that weren't gonna ever be shown to people. All right, so here we go. Type in. I'll show you kind of from scratch. In 10 minutes, we'll be able to do it. So first, type level exercises lists.
Can you make these marks?
Absolutely. Is that good enough, or should I do one more? That's good. Okay. It's a little dark. Yeah, sorry. Yeah. Does somebody want to get the lights back there? Yeah, I think you just press it once and it takes a little while. There we go. All right, great. Okay. So what we're going to do is we're going to implement a GADT that encodes a recursive list structure, like the lists we all know and love in Haskell, but it's indexed by its length. So we're going to define this GADT constructor that's indexed by some type n that has kind nat. And well, since this is ultimately we want to talk about list values, right? That we actually don't want this A to be kind polymorphic. You know, we want to be able to manifest values in this list structure. So what we're going to do is we're going to define the base case where we have like n nil, right? And so does anybody know what type that n nil is going to return? So it's definitely going to be n list. And then what's the first type parameter? 0, right. Yeah, 0. So I am going to remove type nats because it's simpler, and then I'm not going to hide nat. So we can use the nats we know and love. So n list 0, and this is going to also just be the return type A, right? So now we have n cons, and does anybody know what the first argument? Let's assume that like we want to have a value. Well, so we want to have a value of type A, and this is cons onto a list where we have n. We don't know the length of the remainder list of A, and it's going to give us an n list. Now, so does anybody know what the return type of this is? Right, exactly. So we're going to, the return type of the n cons is the successor. Yeah, let's do the tick just for the successor of n and A. Okay, so this is pretty cool. What about the other exercises? Yeah, I'm just going to do lists real fast. There's a lot of stuff still left to do. Just make sure there's not any type errors in my file while I show you guys. Okay, here we go. So now we want to write an append function, right? hopefully you guys know that the head and tail function of this is pretty easy. You just pattern match on cons and just get the head and tail. So the first interesting thing we're going to do with this length index list is to append two lists, right? And to do this, it's going to be a little bit hairy. And we have 7 minutes left, but I think we can do it. We're going to take one list that has, of n length, and we are going to take another list of m length. And I did this just so for the exercises. I thought you guys have a lot of time to do this, but I actually want this to be A. And so now, does anybody know what the return type of this length index list is that we want to return? Right, we want to add these two together. And we want to return the list of the same underlying value type, right?
The add list with capital L, right?
Yeah, right. So we're going to take n. Let's say there's the first case where we have n nil and m. Let's just say n list. And then in this case, we're just going to return n list, right? Yep. So let's see what GHCI has to say about that. Let's exercises basics. Let's do lists. Import type level basics. Oh, right. Sorry, guys. I have to quickly do type level solutions basics. There we go. All right. So it compiles. It likes that. Unfortunately, it won't tell me that I'm missing cases for some reason. Let's see why.
Switch on warnings, maybe?
Oh, yeah. It's GHCI. Yeah. So just trust that it would kind of warn and say that not all the patterns have been matched. So we have n append of nil, and we're going to do the same kind of recursive structure for append. We're going to build this new list, so that's why we're not going to do like n list, n nil, right? We're just going to do, now we have the case for n cons of, we have some value a, and then we have the rest of the list, and then we have some other n list, okay? So does anybody know what we want to put here? So how do we append to lists? Right, so we have n cons of what? A. So we want to still have the first one on the left-hand list, the first value of the left-hand list, we want that. But then we want to recurse, yeah, and we do n append of the rest and then the n list, right? So this is great. You might be like, that's super easy, right? That's really, really easy. But unfortunately, wait, it's working. So I think what I wanted to show you guys is that if we use, so I'm going to be done now, but if you use the GHC typenats library, they implement the logic a little bit differently than we have, and you will get a very annoying error that says, I cannot prove that these two return this type. They'll say, I can't prove that add m, and this is really frustrating that I can't reproduce it. I think if I open up the solutions, I can. So let's just go to the solution real fast. E source type level solutions, and then lists. Okay, E exclamation point, load it. There we go. Right, so this is a little bit more annoying. So you see how I have data type weird. So in this one, I had to do this whole roundabout thing where I have to prove some stuff. Weird. Stick with me for 2 seconds. I will do this and then have the yeah, okay, I'll do this where I have comment this out. I really just want to show you one type error. That's kind of the last thing. I'm going to show you that sometimes when we do this type level programming, it's not all happy and compile immediately, which is frustrating. So we're going to compile this. We're going to keep this as this. We're going to say this is m. And then we're going to do what we just did and say n cons of a and append rest m. And then we are going to do the solutions. Well, this is so hard to see. Huh?
input -4.
I think we'll get the error. Okay, so now I'm not getting an error, so never mind about this. But what I did want to show you, I don't think I wasted your time, because the thing is, now we can encode structures like this. We can encode type-safe indexes, So now instead of n append, we can like enforce the
No, but could you in an append just make an error, like provide implementation that doesn't make sense? Like, for example, for the nil case, return nil. Because that should not compile, right?
Right, yeah, exactly. So let's see that in action.
Make an error. Wait.
So it says, yeah, could not deduce that m is 0 from the context n is 0. So we haven't said anything, since we haven't pattern matched on m, it could be n cons or n nil. It doesn't know. But we're saying that n plus m is, the appending of n and m is going to be the addition of the type indices, right? But we're saying the type indices of nil is 0, right? Obviously the nat is 0. But m could be anything. But we can't guarantee that that is going to be 0, which is the type of n nil that we are returning, right? So this kind of encodes that at that level, at the type level, to make us be able to write.
So that really limits the number of implementations.
Yeah, exactly. Right. So this type level programming lets us constrain the domain of implementations.
It's like dependent type where like kind of a hash version.
Right. We're almost there to dependent typing. Everything I've mentioned today is halfway to dependent types in Haskell. And if you ever read anything about that, all of this is going to be the foundation of it. So yeah, again, thank you for coming. I really appreciated you guys giving me the opportunity to show you this. I had an hour and a half of more stuff that I that I just didn't get to.